Alright, today we're going to be talking about special right triangles. And so off to the left here we have a special right triangle. This is an isosceles right triangle. And so I've got the sides marked congruent here. And so if we know the one leg, we know the other leg. And so because it's an isosceles and it's a right, I know that these two angles right here have to be 45 degrees. And that's because we have 90 degrees over here, and because the sides are the same, the angles across from those sides have to be the same by the base angles theorem. We've talked about that before. So this is what we call a 45-45-90 triangle. And these have special ratios, and we're about to discover those. This is an investigation we did in class. I just wanted to walk you through it in case you weren't here that day, or in case you're listening in. So let's pretend we knew the one leg was 1. That means we know the other leg is 1 because it's isosceles, it's the same length. So then, because it's a right triangle, I can use Pythagorean theorem, which is a squared plus b squared equals c squared. And so in this case it would be 1 squared plus 1 squared equals some c squared. And so 1 plus 1 is 2. So then this is the square root of 2. And so we expand it then and we say, okay, well, what if they were 2? If the one was 2, then the other would have to be 2. And 2 squared plus 2 squared is 4 plus 4, and then I take the square root to figure out what c is. So 4 plus 4 is 8. Square root of 8 splits into 4 and 2. And this is what we call reducing the radical. And it's going to be helpful because the square root of 4 is 2, and so we get 2 root 2. And we do it again. Let's pretend the side length is 3 now. And we get 3 squared plus 3 squared equals 9 plus 9, so 18. Which splits into 9 and 2. The square root of 9 is 3, and so we get 3 root 2. And so what we start seeing here is we got the root 2 and the root 2 and the root 2. And so our hope is that we see this pattern developing. And so I did it again with 7. 7 and 7 make 98. Which splits up into, 7 squared plus 7 squared, 49 plus 49 is 98. And so that splits up into the 49 times 2, because you always get 2 of them because they were the same length, right? So square root of 49 is 7, so you get 7 root 2. So we got 1 and 1, root 2. 2 and 2, 2 root 2. 3 and 3, 3 root 2. 7 and 7, 7 root 2. 8 and 8, 8 root 2. So all of these get a root 2 in there, and you get x and x, and then obviously that would give you an x root 2, following the same pattern than we did before. It also works out alphabetically if you work out, okay, so x squared plus x squared, Pythagorean theorem again, and then, so x squared plus x squared is 2x squared. You can take the x squared out, the square root of that is just x, so you get x root 2. So what we're seeing is that anytime you have a 45-45-90 triangle, the ratios of the sides are going to be 1 to 1 to root 2. Now, it was 2 to 2 to 2 root 2, but all of them reduce so that we get this one special ratio, 1 to 1 to root 2. Some people like writing it with a variable in there as x and x and x root 2, so you can choose either way. This is considered the more reduced form of it because it's taken all the common factors out. And so that's your 45-45-90 triangle and where it came from and the ratio. So now we're going to look at a different one, and that's the 30-60-90. And so the 30-60-90, I've got the 30 is over here and the 60 and the 90. And so let's say that we get the short leg, and I'm going to call the short leg, this is the B. Let's say that's 1. And so what I've done here is I've used dashed lines to take this and reflect it over so that we get a 60 and a 60, and then 30 and 30 make another 60, and so we have an equiangular triangle, making it equilateral. So because we reflected it, this is 1, and so this is 1. And so the whole thing across, 1 and 1 make 2. And because we made it an equilateral triangle, this side has to be 2, which happens to be the longest leg, or the hypotenuse of our triangle. And so I'm going to put my 2 right here. And so notice that if this was 2, then this would be 4, and this would be 4. And so this is always just doubled because we reflected it over. So 5 is going to be double that, you get 10. If you double 2 root 3, 2 root 3 and 2 root 3 make 4 root 3. Now we get the 20 over here, which is a double of the 10. So how do you come up with your long leg? Now we have to zoom back in on the 30, 60, 90 triangle and this long leg of our right triangle. And so we're looking at just this. And so again, we rely on Pythagorean theorem. So what it is now is 1 squared plus something squared, we'll call it a because that's what I called it in the picture, equals 2 squared. So that means that this is 1. So if you subtract the 1 over, this is 4 minus 1, and you get 3. And so a is the square root of 3. So if you do it with this one, 2 squared plus something squared equals 4 squared. So that's 4. That's 4 and that's 16. So you do 16 minus 4 and you get a squared equals the square root of 12. Square root of 12 reduces to 4 times 3. So you get 2 square root of 3. And so 2 square root of 3 is this one right here. And so the idea is that notice that this 2 and this 2 are related. And so the next pattern is going to give you a 3 root 3 and a 5 root 3. And then this one's going to be 2 root 3 times another root 3. So root 3 times root 3 is root 9. So 2 times 3, which is 6. So that one's a little different. And then 10 root 3. So if you do it with x, notice how the hypotenuse is always twice as long. We discovered that first. And that's because of the picture. That we reflected our 30, 60, 90 and made it an equilateral triangle. And so the 1 and the 1 became the 2, which flipped it over. So if this was x, this would be double that, so 2x. And then this would be x times root 3. And so our ratio for our 30, 60, 90, all of them are related to the short leg. And so you get the shortest leg is 1, which is across from the 30. And the longer leg is root 3 times as long as that, which is 60. And the hypotenuse, the longest side in the triangle, is twice that, and it's across from the 90. And so we call this the 30, 60, 90 ratio. And so with the 45, 45, 90 and the 30, 60, 90, you get a lot of possibilities for generalizing what the sides and the relationship of the sides are. And so another way to write this would be x and x root 3 and 2x like we did in our last row up here. Again, this is probably considered more reduced. And in the next video, we're going to practice how to find the missing side lengths in 45, 45, 90s using these ratios. So I just wanted to explain why these were, using some common sense, using Pythagorean theorem, and to show you that 1 to root 3 to 2, and the other one, 1 to 1 to root 2, did not just descend from the heavens on this golden plate while angels sang. And so they actually make logical sense. So try to make logical sense out of them, and you can regenerate them if you forget them in a test situation. Pythagorean theorem is all it takes, and a little puzzling as far as making it an equilateral triangle. Good luck as you work with these.